Good morning, everybody. So, considering the situation in our campus, we will now attempt to have our lectures in an online mode. So, keeping that in mind, today I will share with you the first installment of our online lecture on mechanics of composites. And based on your feedback and based on how it goes, maybe deliver 3 to 4 per week till normal classes resume. And apart from this video, you will also get to see one Google form where if any concept is not clear or if you have any doubt, you can simply write it. I will compile all of them, answer all of them, make a document and share with you 1 week later. So keeping that in mind, today's lecture is about testing of composites. So far we have learned about different mechanics models of composites where the input was either the Young's modulus or the strength or different parameters. But how do we get those quantities? So we will learn about those things in today's lecture and maybe the next lecture. The entire module is divided into two halves. The first half is basic idea about testing of composites, why we test, how we test, etc., etc. And then the next lecture, which is perhaps tomorrow, will be about specific cases, how to calculate the tensile properties, how to calculate the bending properties, and so on and so forth. So the outline of today's lecture is, first we'll understand why do we need to perform a test. Some of the reasons are obvious, some are not so obvious. We will look at that. And then what are the different scales of testing? Are we talking about testing of a coupon? Are we talking about testing of a fiber? Or are we talking about testing of a component? How are they different? When to do what, etc. After that, what determines a good test method? It's easy to do a test, but how do we believe that a certain test was done properly? If, let's say, if I tell you I have tested a material and the property is this, will you believe me? And when is test result equal to material property? What are the conditions that must be satisfied? Finally, some specific nature of composite materials. Testing an isotropic material is different than testing an anisotropic material. And then we have some test standards. Finally, the conclusions. So, why do we need to perform a test? What are the different reasons? The first reason is to develop a new material, you want to do some tests. You want to test a fiber, you want to test a matrix, let's say make a composite, have some ideas about, at the development of the material stage, you have to perform tests. You also need to perform tests to do some theoretical work. Sometimes tests are the starting point of theories. You do some tests, you try to understand the physical phenomena and then build your theory around it. Or on the other hand, you want to use such methods to verify your models. For example, consider we have developed the classical lamination theory. It was based on some assumptions. You get some properties of effective stiffness. Now, how accurate is this? Can we use it reliably? No amount of math can confirm whether or not a model is valid. You need to back it up with some tests. So that could be one reason for doing a test. Other reason could be comparison with metals. So throughout our lecture, quite often we have compared our composite materials with aluminum, for example. How do I know the property of aluminum vis-a-vis how do I know the property of a composite? How can I make that comparison? And if I cannot make the comparison, how can I say which one is better than the other for some other reason? So comparison with other materials is also a very important reason for performing test. It could also be input for design calculations. So you can, let's say you want to use the rule of mixtures, and to use the rule of mixtures, you need the properties of the fiber and the matrix. For that, we have to perform a test. Or it could be for prediction of performance in real life. So let's say you used carbon fiber or some other composite, built a part. How long is it going to last? Or let's say I make a plane out of carbon fiber reinforced composites. After how many hours of flying should I not use that plane? And the final reason could be quality control and assurance. For example, if I make a part out of a carbon fiber composite, will it have the same property every time? Right? So, am I assured of a certain range of quality? For example, we discussed in the class few weeks ago that the aerospace standard is that if you make a composite, the void content should be less than 0.25%. Otherwise, it is not considered good enough for aerospace. How did they arrive at that number? they must have performed some tests. Now, the first step is you determine the goal of your test. The goal of the test will determine the type of specimen. Do you do the tests on a coupon, on a substructure, the whole structure? You also have to decide, depending on the goal, what are the environmental conditions. Are you going to do very precise, accurate lab control where you control the humidity, the temperature, or you do it more like real life where the temperature could vary in a range, there could be dust, so on and so forth. What are the environmental conditions that you will choose? What is the test equipment we'll use? Can you use a general purpose machine, or do we have to design a dedicated structure test rig? And finally, last but probably not the least, is the data reduction. Is it okay or not okay? That is one way of looking at this. I do a test and I have a binary question in mind. I want to test my material and then I see whether or not my material is okay for using, or my structure is okay or not okay. Or we could be looking at some basic data, like I'm not interested whether or not a carbon fiber composite or some other composite is suitable for use, but I want to know the basic properties. I want to know the Young's modulus, I want to know the strength, etc., etc. Or the third could be, do I need to do full data acquisition? How much data can I extract from a single test, and what are the different accessories that I need to use? For example, if I'm doing a test on a coupon, most likely I will also put an extensometer, or I will use digital correlation. But when I'm doing the test for a component, for an aeroplane wing, for example, I will not do these things. So first of all, you will determine the goal of your test, and once you determine the goal of the test, there are lots of design decisions that you have to make. Let us take the example of a offshore application of composite, which is a glass fiber reinforced pipe. They look like the image. So let us say normally these were made of aluminum and you want to replace them with glass fiber reinforced plastic. So before replacing, what are the different tests that you have to do? First of all, you will do a coupon test. A coupon test is basically some sort of a flat sample where you make a flat sample and you apply a force. I'm sure most of you have done this or seen some type of tests. The goal for coupon level tests is material selection. You want to determine the strength, stiffness, toughness, maybe compare it with aluminum, see how different is it to justify your material selection. What type of test you will do? So when you do a coupon level test, it is going to be almost ideal conditions. It's going to be in a controlled lab where the moisture is controlled, temperature is controlled. Maybe you'll put it in an environmental chamber and say that the temperature should be so and so degrees Celsius. The loading is going to be simple, as in uniaxial tension or very low strain rate, and you will do extensive data reduction. Meaning from a single test you will try to collect large amount of data. For example, if you do a normal tensile test, from the stress strain curve you could extract the Young's modulus, you could extract the yield stress, you could extract the toughness, you could also extract the Poisson's ratio. So at a coupon level test, with one test you want to do many things. And the coupon type will be a small one component, simple small specimen, usually rectangular, but the specimen preparation will be ideal, where you will get very strict rules about, there are strict standards about what the length should be, what the breadth should be, how much is the tolerance, there should be no delamination, there should be no voids. So you have to take a lot of care in trying to make as ideal a specimen as possible. But the good thing is it is simple and small. So after you have done your coupon level testing, you are sure that it's a good enough material, then you have to do part testing, where instead of the entire pipe, you will take a small pipe and you want to do some tests. In our application case, the different cases will be fatigue test of a tube. So when gas is flowing through the tube, it might be subjected to fatigue law, or when the pressure is too high, it might burst. Or you have two pipes which are joined to each other. What is the strength of the pipe joint? So these are the different things that you have to think. So when I'm doing part testing, I will have certain goals which will be very specific to the application, as opposed to our previous test where the coupon test was more general. What will be the testing condition? Again, it will be almost ideal condition because it's a part, not the entire structure. And the loading case is not as simple as that for a coupon, but significantly easy to execute. For example, I will do a simple sine wave fatigue loading with frequency rate exactly same, and my data reduction will not be as extensive as done for coupon tests. Type of coupon will be, there will be limited number of components. It could be where I have more than one specimen joined together to make a coupon or a testing specimen type. And once again I have to be careful, but the specimen preparation rules are not as stringent as the one for tests at the coupon level or the test at the material level, but you have to be careful. And the size of the specimen generally increases when you go from material to part. The third is the structure testing. So I have tested my material, I have tested my part. Now so far it meets my design requirements. What do I do next? I design a structure and test it. And this time my goal is to test of whether the prototype that I have built is good enough. And the aim of this test is to decide okay or not okay to use the design structure for my tests. And even though I am describing these three levels of tests as three unique steps, but they are interactive. For example, let's say you did the material test, then you did the part test, and then you did the structure test, and in structure test you decided not okay, that somehow the structure you have designed is not meeting the requirements. Then you will go back and then you will find out that you will try to back calculate what should have been the properties so that my structure was okay, and then we redesign the material and then repeat the tests. So there is several iterations between the three stages of testing. And testing conditions now get much more difficult. For example, you might have to design a special test rig. For coupons, usually you have your ASTM standards and rigs are there in almost every lab. You can go to the lab and test it. But for a component, you have to design the test rig, which is a difficult activity. And the conditions are real conditions. You don't want to control the moisture and temperature. You try to make it as real as possible as opposed to ideal. And it can be very complex loading condition where you actually collect data from a real application and you subject that data. So yeah, the testing conditions is that you might have to design a special rig, as I just said 5 minutes ago or a few minutes ago. And the problem is the very complex loading conditions. So typically when you are testing a real structure, it is to replace an existing structure, and when it is replacing an existing structure, the data of the loading is available for that existing structure, and you have to replicate the exact same loading in the part that you have designed to prove that your new material, your new design is actually working. And there is no data reduction as such. You just say, look, for the loading type, aluminum survive n number of years and composite survives m number of years, where m greater than year n, so this is okay, vice versa not okay. And coupon type, you will have many different components which are joined together. If you just Google and if you say Airbus A400M wing testing, so you will see lots of results about how it is tested. It's a really big structures can be tested nowadays. Structure is prepared as in real life, so there can be defects, there can be welds, rivets which are not ideal, uneven surfaces, etc. And specimen is usually quite large. If we take our example, for the material selection, coupon will be about 250 millimeters, maybe part will be, let's say, a meter, and the structure could be tens of meters to be tested. So there are different size of components, you need different lab facilities, and there are different challenges at every stage. Now, if you recall our case study 1, we had discussed that there was a coupon level test to find the material properties, but there was also a component level test. If you remember, we have done this where this is my Pinocchio, as we had called it. This is my industrial test case. This is the special rig that was designed, but the coupon level was a rather simple coupon which was tested based on some ASTM standard. So the next question is, what determines a good test method? The first important condition that every test must satisfy is that the result must be representative. It must be representative for the component. For example, if you say that 50% carbon fiber and matrix was used and this is the property, then your property must be representative for 50%. Anybody who tests 50% carbon fiber and that same matrix should get the same property. It should also be representative of the processing parameter, the shape of the coupon or the size. In this, I think you can recall your term project where you dealt with size. Why size is important too? That if I have a small coupon level, my results will not be representative. If I have big enough, then it is representative. So a good test method ensures that your results are representative. Representative also for the humidity. So you cannot just say that I have a sample and my modulus is 100 megapascal. You have to specify how it was made, what was the thickness of the sample, what was the size, temperature, humidity, loading condition. Because the properties of a material, especially a composite material, will vary wildly according to these factors. You have to, a good test method will specify everything and the result will be representative of all these factors. Now, and if you do everything right, the test result will be your material property. Meaning that the data that we have got for your material is actually the data of that material as opposed to the data for a very specific test that you have done. So there should be, so that somebody else has tested that material and there is a property and some standard deviation and your values should be in that range. So you should have some level of confidence. At the end of this lecture, we will discuss about how confidence limit is calculated and I will dwell more upon this aspect. So is test result equal to material property? Test result is usually not equal to material property because of various problems. Test result and material property can be different if your specimen dimension is very small. As a rule of thumb, your specimen dimension should be much bigger than your scale of inhomogeneity. If my carbon fiber is 50 microns thick, my specimen cannot be 100 microns thick. It has to be 100 into some big number. You should have a uniform stress field. So when you do a test, there is some area called the gauge length where all the measurements are done, and in the gauge length you must have a uniform stress field. It cannot be that there are different states of stress at different points, and in that case your strength values are not accurate, because if there is no uniform stress field then there will be local damage. Another problem is that you should avoid end effects. Your sample should not fail at the end. At the end, obviously there are going to be stress concentrations or defects due to your manufacturing process. So in the field of composite, this is a very important criteria. How do you find out that in the gauge length, in this area where all the measurements are taking place, there is a uniform stress field? And of course, your test should be repetitive. Let's say you go to the lab, you do a test and you record it well. Now, I should be able to go to the lab. If I repeat everything that you have done, I should get the same results. It should not depend on the skill of the operator. It should not depend on the machine even. Let's say you did a universal tensile test using Instron machine, you got some properties. If I do the exact same thing in some other brand or some other machine, I should get the same properties. If that is the case, then we can say that the test result is actually your material property. Now, all this is a problem especially for composite materials because your properties depend on so many things. They depend on the fiber, the type of fiber, the size, orientation, volume fraction. They depend on the matrix, which matrix are you using. Even for the same type of thermoplastic or some type of thermoset, there can be wide range of properties. For example, if you look at polyamide, polyamide has property variation from about 1 gigapascal to 5 gigapascal. So not only do you need to know that it is polyamide, you also need to know which blend of polyamide. There is large variation. Then there is the question of fiber matrix interface. Did the fiber and the matrix glue to each other properly? And you also have to account for laminate stacking sequence. So when you say that the property of a composite material is XYZ, That is an incomplete statement. You should say XYZ, the composite is made of this fiber, this orientation, this fiber volume fraction, this matrix was used, this is the sizing that was done, and this is the laminate stacking sequence. Only then is the information complete. Usually we neglect this description. This is because we assume that the fiber matrix interface is perfect and that the chemists and the material scientists have done their job. But other than this, you have to be sure about each of the different factors. And the specimen itself, let's say you have accounted for everything, you've recorded everything. There is the importance of edge. At the edge, there is chance of delamination, like shown in the figure. And there is also what is known as the pure scaling effect, which I will discuss in the next slide. The scaling effect says that if you have a brittle material like glass fiber, then they will follow a Weibull distribution, which says that basically that if you take 100 fibers and test them, fibers are usually brittle, the strength and the modulus will not be constant, you will have some variation, and this variation is following a Weibull distribution. And you can calculate the probability of failure at stress sigma by using a formula as given in the slide, where sigma 0 and alpha are your Weibull parameters, which are experimentally determined by large number of samples, and V is your specimen volume. And why is specimen volume important? Specimen volume is important because now because per unit volume the number of fibers will increase. If I have a very small volume, the number of fibers will be less and I will get large amount of scatter in the tests. For example, look at the plot. In one of the y-axis is the tensile modulus in gigapascal, one of the y-axis is the tensile strength, and the specimen scale. How big is the specimen? So as I increase the specimen scale from 1 to 2 to 3, the tensile strength is increasing. But after some time, it more or less plateaus out. So to do a correct test, my specimen scale should be at least this, because after this the properties are almost same. Same for tensile modulus. If my specimen size was smaller than this, let's say it was somewhere here, then the properties are actually not the properties of the material. Depending on how much tests you have done, depending on who did the tests, you will have some scatter and you are under predicting or over predicting the values. Another problem is your severe end effect. Near the sample end, there are going to be inhomogeneous stress field. Inhomogeneous stress field means, as I said, in the gauge length, you want the state of stress to be uniform, so that then you can average whatever material or whatever stress is there in the entire gauge length and then relate it to the modulus. However, for anisotropic materials, usually at the edges you will have some sort of inhomogeneous stress field leading to failure at the edges. As a rule of thumb, the gauge length of your specimen should be the width into square root of Young's modulus by Shear's modulus. So for an isotropic material, E by G will be roughly 3. So the length is expected to be 1.7 times the thickness or the width. So if you go to our material testing lab, you will see that the test samples for isotropic mild steel is about this, which is like 10 centimeters. But for unidirectional carbon fiber epoxy for volume fraction 0.6, Young's modulus by Shear's modulus is about 35. So the length has to be about 6 times the width, and the width is about 20 millimeters because of the inhomogeneity condition. So you'll have very flat long samples. This is a specific difficulty with anisotropic materials. In general, if you are testing an anisotropic material, the length of the specimen is going to be much more than the width, 5 to 6 times. And if you compare with an isotropic material, the samples are usually smaller. So other difficulty with anisotropic materials is premature failure in the grips, which is much more pronounced than isotropic materials. There are delaminations and there are unintended failures. Let's say I am taking a material, I am applying some sort of compressive load, I want to check the buckling strength. Now my fibers were misaligned by some angle or my load was not properly aligned, it failed due to shear. Now if that happens, then my test is incorrect, I have to repeat the test. Either I have to repeat the test or I have to do detailed analysis of the loading condition and then understand why this happened. Another big problem is, let's say I want to calculate the shear strength. We'll discuss more about it in the next lecture, but how do you calculate the shear strength? You do some tests and you apply load such that your material fails due to pure shear. And you do your test, but because your material is anisotropic, it was not as predicted and your material failed due to tensile failure, or vice versa. Then there are problems in your tests. You have to repeat your test after some detailed analysis of the loading condition. So basic elastic and strength values of isotropic materials, as you have discussed in class. Isotropic materials, usually two elastic properties are enough. Usually you do a single test, you can calculate the Young's modulus, you can calculate the Poisson's ratio. And strength also, usually you have one or two. You have tensile or compressive strength and you have yield strength. So the number of tests that you need to do is limited. Most likely by two tests or two sets of tests, it should be enough. One tensile test gives me Young's modulus, Poisson's ratio and the tensile strength, and a compressive test which gives me the equivalent properties. Now anisotropic materials is much more complex. If you recall from our class, an anisotropic material can have as much as 21 elastic constants that you need to calculate. Okay, and the strengths will be even higher. So elastic properties of anisotropic materials are still possible because it's a bulk property. So stiffness is an average property. You could, by doing 6 or 8 sets of tests, perhaps you could calculate. But you have to keep in mind that the number of constants is high. If it is anisotropic 21, transversely isotropic 5, orthotropic 9. Strength is even more tough because strength is a local property. It is very defect sensitive. It is very fiber alignment or small defect errors in your manufacturing and your strength goes off. So you will get a large scatter. Large scatter means, let's say I do 5 tests and the modulus is likely to be, let's say, 1000, 990, 1010, 1005 in a very narrow range, 1000 plus minus some standard deviation. But strength could vary from 100 to 500. So it could be 100, 250, 300, 500, 450. So you have a large scatter because sometimes it failed unexpectedly. And long-term behavior like fatigue or creep is even more difficult for anisotropic materials. So strength of composites, you need 9 values, which we have already discussed in the class. You have 3 tensile strength, 3 compressive and 3 shear. And for each of the tests, sometimes you have to do about 50 or so, 20 or so tests because of the large scatter. It just depends. There are various ASTM standards telling you how many tests should you do and whether you should average or what. But from the previous slide, the number of specimens to be tested to get the complete strength properties of an orthotropic material is 9 into n, where n can be any number between 5 to 20. Okay. Right, so now let us go, how do we prepare test specimens? Test specimens can be prepared by various methods. You have to decide depending on your application, depending on various conditions, the goal of the test which we have discussed previously. Now, a big problem is variation. Variation will depend on the local material property, that fiber alignment, void defect. This is directly dependent on the manufacturing method that you have chosen. It could also be, variation can also come due to the test conditions. Let's say you did not align your 0 degree sample to the loading, there was a slight misalignment, or there was moisture or temperature during the test. Tests done in the winter versus tests done in the summer in a non-air conditioned lab will be different for composites. So there will be a lot of variation and you have to be careful about it. So there is a large scatter and many specimens, sometimes up to 20. So behind my photo there should be the number 20. So you can now, I think, imagine that the large number of tests that you have to do. That's why the last point that I made in our previous point is that sometimes material is chosen not because it has superior properties, but because the material properties are available. Because it is difficult to make so many samples accurately. It is difficult to do the test and then also collect the data. It is difficult, it is expensive, it is time consuming. Now let's say you have a variation. What do you do? First of all, you will calculate the standard deviation. You have a mean and you have a standard deviation. This is a standard formula. And then you calculate the confidence limit using what is known as a T students distribution. So you get a list like this where N is the number of samples, how many samples you test, 5, 6, blah blah, and what is T by root n for 90% confidence. And in this formula, sigma is your standard deviation. So based on this, you get the confidence limit for 90% samples. What does confidence limit? Confidence limit assumes that if you do a large number of tests, then the frequency curve is going to follow a normal distribution. And you are trying to calculate the two bounds in your normal distribution such that a certain percentage of samples are in this range. It could be 95%, it could be 90%. So this is the calculation that you are trying to do. So instead of saying that my average is this value, you will say that average plus minus this number, whatever you have calculated, is the confidence. So you can say, you can say with 95% confidence that your material property is mean plus minus the range that you have calculated. Let us take an example. Consider that you did 30 tests and the average strength you calculated was 175 megapascal. And you found out that the standard deviation is about 20. Okay. Now if you look at our previous slide, confidence limit will come out to be plus minus 7.4. It means that 90% of samples will fail in the range 75 plus minus 7.4 megapascal. So while doing design, most likely you will base your strength not as 175 but 175 minus 7.4, because you know that at least 90% of the samples have 175 minus 7.4 or more. So your design is conservative. This idea can also be extended to fatigue testing. In this plot, you will see that the solid line is the markers are the data. The solid line is you curve fit it to some exponent power equation and you calculate the 90% confidence. So 90% of the fatigue data is in between the two dotted lines for each of the three cases. And if you wanted to do a design, you just look at the lower line. Then you are sure that 90% of the samples have at least this life or more. And this idea of confidence limit can be extended for any material property that you test. It could be Young's modulus, strength, fatigue data, anything, or bending data, etc. So keeping all this in mind, now there is a requirement for a test standard. Let's say you test some material in Nigeria, I test the same material in India, somebody else tests the same material in the US. We should have trust among each other. I should believe that the tests done by so and so in XYZ lab is representative of the material, so that all of us do the tests in the same way, and then nobody needs to do all the tests by himself. He can simply say, okay, so and so has followed this standard and this is the property. You can take that value for your design. So while designing test standards, usually there is a compromise between accuracy, repeatability, and cost and simplicity. You want the material to be, you want the test to be as accurate as possible, as repeatable as possible, but you want the cost and simplicity to be under control. So usually there are standards which will tell you that if you follow my standard, then the repeatability is n percentage, where n is mid 90s or high 90s. And usually such tests should not be very expensive to do. We will discuss some test standards in our next class. So there are different standardization bodies. There are some international test standards like ISO. ISO test standards are standards which are followed internationally but has no legal implications. For example, if I say I have developed this material, I tested by ISO standard, modulus is this, and somebody later finds out that the modulus is not that, then I cannot be sued. There are also what are known as supranational test standards across multiple countries. Like CEN is, I think, the test standard across Europe. And you have what are known as national test standards. ASTM is the American, DIN is, I think, German, GIS is Japanese, BS is British standards. So different countries have their test standards. If I want to convince a British manufacturer about the properties of my material, I have to do the test according to BS standards. And when in doubt, usually we go for the ASTM standards. And at IIT Kharagpur, we have access to the ASTM standard. So it might be interesting for you to just go to the internet, browse ASTM standards and just have a look what a test standard looks like, what are the information that is given, etc. Some test standards are also sectorial, that Automotive sectors would like the test to be done in a certain manner, aerospace in a certain other manner, defense has its own test standards, and there are also company-wise test standards. For example, in the aeroplane sector, there are two fierce competitors, as you all know. One is Boeing, the other is Airbus, and they have their own test standards. So Boeing does its tests in its own way, Airbus does it in its own way. As a material supplier, once I have the experience that we did all our tests according to the Airbus standard, and the sponsor of the project wanted to pitch that material to Boeing, and they would refuse to take the material properties seriously because they were not done according to their standards. That is the standard that they have thoroughly tested, that if you do the test in that certain manner, the properties are reliable. They don't trust anybody else. So there are different standards. You have to choose one based on your application, based on your customer, or based on the OEM that you work for. But these are there to help us. It is not like I have to start from scratch. If I want to calculate the Young's modulus of a carbon fiber composite, I don't have to start and guess that, okay, let me take a sample size ½ inch, calculate the scatter. No, scatter is too high, let's do 1 inch, calculate the scatter, etc. I don't have to go through the iterative process that you went in your simulation. There are standards. I can just open up the standard and I say that I am doing the test according to, let us say, ASTM standard. There, the clear definitions about what the length, width, thickness, etc. will be provided. So this brings us to the end of this lecture. And what are our conclusions? Conclusions are that a test result is a mean value plus minus standard deviation. So far in our class, we have said that the modulus is a number, the strength is a number. This is useful to do our calculations and for learning theory about certain concept. But in reality, you should never say that a test result is a value. It has to be a value plus minus standard deviation, because you will always get scatter, especially for anisotropic or orthotropic materials. Composites will show large variation. It depends on fiber alignment, whether there are voids, defects, specimen is misaligned. So since there is large scatter in results, you have to do many tests. If you want to find the properties of aluminum, 1 or 2 tests are enough. Similar property in composites, you are looking at least 5 to 20 tests. Composites suffer from their anisotropy. Due to anisotropy, there can be unexpected failure modes, there are edge effects, end effects, so many things that you need to consider. So you have to take special care in the selection of the test method. You have to be very rigorous about how you are doing the test, which test standard you are following, read that thoroughly and try to follow it as in depth as possible. Okay, so that brings me to the end of this lecture. The next lecture is going to be on actual mechanical testing of composites, where we learn how a tensile test is done, how a bending test is done, etc. etc. Thank you for your attention.